Morning, girls. This video is about some patterns that you'll find in probability. I find probability to be quite a tricky concept because in some respects it's about time travel or alternative universes. What you're seeing in front of you is an alternative universe or a set of alternative universes where you might pick an apple or a banana. It's just a really simple example. So how can we pull this apart? So here I am. I'm starting in, I don't have my apple or my banana here. So anything can happen. And I reach out into the universe and I can either have an apple or a banana. And here's my result. I either have an apple or a banana. I've taken one decision. So in universe A, I've got a banana. And in universe B, apple. In universe B, I've got a banana. Every time I reach out, I take an extra step, a new possibility could occur. So if I follow this tree diagram along, I could, in one universe, have apple, apple, another one have apple, banana, third universe, banana, apple, fourth universe, banana, banana. Notice how I'm not kind of worrying about the chances. I'm not worried about what are the chances of getting an apple, what are the chances of getting a banana. I'm just looking at what's known as the combinations. These are the combinations of things I could have. So I've had one choice, I've had two choices. In this second choice, I could either have apple, apple, banana, banana, or once I've got my two bits of fruit, this thing here, these two outcomes are virtually the same. I've got apple, banana, or banana, apple. Now we know algebra. If I was multiplying these probabilities together, then I would have two lots of this apple, banana. This will become important later on. Okay, so let's look at this. I've chosen 3 bits of fruit. Now the outcomes, yeah, they get to be an awful lot of them very quickly. We had 2 possible outcomes, then we had 4 possible outcomes. Now I've got 8 possible outcomes. How many are repeats? Let's have a look. Well, there's only one of these, apple, apple, apple. I'll use red for that one. There's only one of these where I could pick 3 bits of fruit and they all happen to be apples. There's only one of these where I pick 3 bits of fruit and they all happen to be bananas. But how many outcomes from choosing 3 bits of fruit would give me 2 apples and a banana? 1, 2, 3. Okay, come on, computer. Computer's being stupid. All right, so I've got 3 of these outcomes that could be 2 apples and a banana. And I've got also 3 of these outcomes where I've got 1 apple and 2 bananas. Yes, I am going a bit bananas. Look, we are going somewhere with this. What I'd like you to do is imagine the next branching of this tree. We'd have 16 different outcomes. How many of those outcomes would only be apple? How many of them would only be banana? Now, if you like, you can pause the video and actually work that out. It might be a good thing to then write it out in this form here. So if I did it for this here, I'd say I'd only have one of these apple, apple, apple. Now we could write that as a to the power of 3. I've only got one of those. How many of these AABs? I've got 2 of these apple, apple. So a squared banana. It's very difficult to do this without a pen. I've also got 2 of these. I'll do this in light blue. 2 of these apple, banana, banana. So 2AB squared. And I've only got 1 of these banana, banana, banana. So I don't need a 1 in front of that. So what you might like to do is at this point pause the video, try and work out the next branching. There will be 16 outcomes. You'll need a fair bit of space. And then write down how much of each kind of thing you've got. Now you can either choose to do that or you can just keep listening to me as I rant on about probability. Okay, here we go. So what I've got here is something you might find familiar. They're called binomial products. They're binomial because there's two. Here's my apple and banana again. Now I'm just going to slightly shift this and add something. We can see a pattern here. 5, 4, 3, 2. Well, this must be 1. Let's change back to black. And we can also have, and I'm going to dodgily write this with my finger, a plus b to the power of 0. That's a 0, not a 6. Dear, oh dear. And that one I'm just going to write straight away. That is a 1, because anything to the power of 0 is 1. This one here would be a plus b. Now these other ones you could do, but you will know that as soon as we get to the power of 4 and then to the power of 5, expanding them out and collecting like terms can take an awfully long time. Luckily, I've done it here for you. Now, does this seem familiar? To the power of 0 is kind of a way of saying if I haven't done anything, I've got a probability of 1. Now, I am going to return to that idea in the future, but for now, we're just going to have to trust that it means something and move on. If I've made one choice, I could have an apple or a banana. If I've made two choices, well, I could have apple, apple. There are two ways I can get apple, banana, and there's one way I can get banana, banana. This is known as binomial expansion, and you'll see that the pattern we were hinting at before with our tree diagram is here now. So if you chose 3 things, this is the end of the one we did together. There's only one way we can get 3 apples. There's only one way we can get 3 bananas. There's 3 ways we can get apple, apple, banana. There's 3 ways we can get apple, banana, banana. All right. Now, the wonderful thing about this is it allows us to take some shortcuts. Looking at the power here, if I didn't want to expand out a plus b to the power of 4, then I know there's only one way I can get a to the power of 4. There's 4 ways I can get a to the power of 3b. There's 6 ways I can get a to the power of 2b. There's 4 ways I can get ab to the power of 3. And so I can take a shortcut and just go, well, the power is going to be 4, then it's going to be 3, 1, then it's going to be 2, 2, it's going to be 1, 3, and then it's going to be 4 at the end. So the pattern is, the power here tells me the biggest power at each end, and then I just lower that one and raise that one, because what's the power hiding there? Power of 1. I lower this one and raise that one. I lower this one and raise that one until it kind of shifts from all the power being there to all the power being there. So this is how I can start with a plus b to the power of 5 and make the pattern of powers without having to do any expansion. But how do we find these numbers in the front without having to expand it out? All right, well, I'm going to show you something that's really cheeky. This thing. You might remember this. This is Pascal's triangle. There's our 1 at the top. Now, how do we use this? Well, that could be 1 apple, 1 banana. Or rather, this is how many of each kind of term we're going to have. When we went a plus b to the power of 2, or rather we chose fruit twice, we had 1 lot of a to the power of 2, we had 2 lots of ab, and we had 1 lot of b to the power of 2. Look at this line down here. This is this was squared. This line here is cubed, or choosing 3 times. This one here is to the power of 4, or choosing 4 times. And what's happening here is this line here is a plus b to the power of 3. I've got 1, 3, 3, 1. And let's go back a little bit. 1, 3, 3, 1. Don't forget there is an invisible 1 hiding in front of this. and in front of this. So how do we get these numbers? 1, 4, 6, 4, 1. This is to the power of 4. So 0, 1, 2, 3, 4. I go down to the fourth layer deep in our Pascal's triangle, and I should see the numbers 1, 4, 6, 4, 1. Do I? 1, 4, 6, 4, 1. So what we're exploring here at the moment, girls, is how to choose objects from space and work out their probability. Now, we haven't assigned any numbers to the probability. We haven't said there's 40% of getting an apple or 60% of getting a banana or anything like that. What we're trying to do is work out the base pattern that will allow us to apply probability to choosing objects. At the moment, you don't have to memorize this. You don't have to master this. It's a concept. Let it just swim around for now, and I'll make another video in a little while and show you how we can use this to work out probabilities in what's known as combinations. All right, I hope that was at least interesting.